Welcome to the Explainer. Today, we're going to break down Big O notation. It's basically the language we use to measure how efficient our code is. So if you've ever looked at two pieces of code and wondered which one of these is actually better, well, you are in exactly the right place. So let's imagine this. You've got two different functions. They do the exact same thing, they both give you the right answer. But how do you really know which one is more efficient? Which one is actually faster? Especially when you're not just dealing with 10 items, but maybe 10 million. Yeah, looking at these two, your gut is probably telling you that code B is doing way more work. I mean, that nested loop just looks more complicated, right? But to really understand the scale of the difference, we can't just go with a gut feeling. We need a real system, a formal way to measure the stuff. All right, so here's our game plan. We're going to start by defining what Big O even is. Then we'll take a tour of the most common runtimes you'll see. After that, we'll pit two algorithms against each other and see what happens, and we'll wrap up with the bigger picture. Okay, first things first. Let's get a solid handle on our main topic today, defining Big O, which is really the language of efficiency. So what the heck is Big O notation? Put simply, it helps us answer a really important question. If I double the amount of data my program has to chew through, what happens to the time it takes to run? Does that time also double? Or does it quadruple? Maybe it barely even changes at all. It's all about describing that growth rate. Now, believe it or not, Big O actually has a few cousins. You might hear people talk about Big Omega, which is the best case scenario, or Big Theta, which is kind of the average case. But honestly, in the real world, and especially in job interviews, we almost always focus on Big O, because we want to plan for the worst case scenario. We want to know just how bad things can possibly get. So here's the absolute key to understanding this. When we calculate Big O, we get to simplify things a lot. We drop all the constant numbers, and we only pay attention to the one part of the equation that grows the fastest as our input, n, gets huge. In that first example, yeah, 100n seems like a lot. But as n gets bigger and bigger, that n squared term is like a rocket ship. It's just going to leave the 100n in the dust. And that's all Big O cares about. All right, now that we've got the basic rules down, let's go on a little tour. We'll look at the most common Big O types you'll run into, starting with the fastest and climbing our way up the ladder of complexity. We'll start at the very top with the absolute best of the best, the holy grail of efficiency, O1, also known as constant time. This is the goal. What this means is pretty mind-blowing. The algorithm takes the exact same amount of time to finish whether you give it one piece of data or 1 million pieces of data. A perfect example is just grabbing an item from an array using its index. It doesn't matter how big that array is, the computer knows exactly where to go, so it takes a constant amount of time. Next up is O of log n, or logarithmic time. This one is also incredibly efficient, and it's a real lifesaver when you're working with gigantic datasets. The secret sauce for logarithmic algorithms is that they work by cutting the problem in half over and over again. It's just like searching for a name in a phone book. You don't start at A and read every single name, right? Of course not. You open it up to the middle, see if the name is in the first or second half, and then you've just eliminated half the work in one step. It's brilliant. Okay, now for one of the most common and intuitive complexities you'll see everywhere, O of n, or linear time. And this is exactly what it sounds like. The relationship is basically 1-to-1. The runtime grows in a straight line directly with the size of the input. So if you have to process twice as many things, the code takes about twice as long to run. Any simple loop that has to touch every single item in a list is a classic O of n. Okay, now we're venturing into the danger zone. We're talking about runtimes that can get slow, and I mean really slow, very quickly. This is quadratic time. You usually run into this disaster when you have a loop nested inside another loop. It means for every single item in your list, you have to go through the entire list again. The runtime here just explodes. If you double the input size, the runtime doesn't just double, it quadruples. This is the kind of thing that can bring a whole system to its knees. So, theory is one thing, but let's see how this all plays out in the real world. Knowing the rules is great, but applying them is how we make smart decisions about our code. So on the surface, this looks like a no-brainer, right? We just went through the ladder of complexity, and O of n is definitely simpler and therefore faster than O of n log n. Or is it? Okay, let's look at the actual math behind two algorithms. Algorithm A is O of n log n, and B is O of n. But look closer. See those numbers out front? The 5 and the 25?
Those are called constants. And you'll notice algorithm B's constant is a lot bigger.
And this is where it gets really interesting. Because of that huge constant factor of 25, when you're working with smaller amounts of data, algorithm A, the one with the worst big O, is actually faster. That constant totally dominates the equation when n is small. In fact, for these two, it's not until your input size hits 100,000 items that the faster growth rate of O(n) log n finally catches up and algorithm B pulls ahead. And this is such a perfect illustration of what Big O is really about. It's not about which code is faster for 10 items, it's about predicting how the performance will behave at a massive, massive scale. So, after all that, what are the most important things to remember? What's the big picture here? Let's just drill this down. Remember these key ideas. First, Big O is all about that worst-case growth rate. Second, you always focus on the dominant term, the one that grows the fastest. Third, for really big data sets, a lower complexity is almost always going to win. And finally, as we just saw, don't forget those constants. Real-world performance is a mix of the Big O theory and those pesky constant factors. And that leaves us with one final classic dilemma in computer science. A lot of the time, the fastest algorithm, the one with the best time complexity, gets its speed by using up a ton of memory. This forces you to make a choice. Do you want to optimize for speed, or do you want to optimize for memory usage? It's this eternal balancing act, the classic time-space trade-off, and it's a puzzle developers have to solve every single day.